Wow. So it's all been building up to this. The fundamental theorem of calculus. This is actually an amazing theorem. And there's really two parts of it. We're typically going to use the fundamental theorem part 2 a lot more than we'll use part 1. If I get a chance towards the end, we'll do a problem or two from part 2 or part 1. But as we were discussing just a moment ago, yeah, this is going to put the fun in these calculations. So now, what this says is if you have a continuous function and you want to find this integral. Now, what's that integral represent in terms of a graph? The integral from a to b of f of x dx. Yeah. It's the area underneath a curve between points A and B. So it's just going to be this area right here when you've got y equals f of x between A and B. If you want to find that area for whatever function, then all you're going to need is a nice continuous function and an antiderivative of that function. If you have the antiderivative of that function, call it capital F, then to find this integral, all you're going to do is find the function evaluated, or the antiderivative evaluated at the endpoint, minus the antiderivative evaluated at the other endpoint, f of b minus f of a. And that's it. Wow. That's going to really change your work. That's so cool. So let's start with this one here, because it's kind of basic. Now the dx term, I mentioned that in section 5.2. That's important because it tells you what you're integrating with respect to. You want to find an antiderivative for this function, something that you differentiate to get this function. What would be something that you would differentiate to get e? X times e. So our function is going to be ex. Now you could put in a constant here to kind of make it a more general derivative. Let me make that look a little bit more like an e plus c. And we're going to evaluate that at -4 and 4. So that's the notation. Notice something different about the way I wrote this. This is no longer an integral sign. It's a straight up and down bar. So, okay. So let's put in the 4 from the upper limit. So it's going to be e times 4 plus c plus e times -4 plus c. Let's see, there should be a minus sign in between these things. And I think I've run out. I hate when that happens. All right, so there's a minus sign in between here. So what am I going to be left with? It's going to be 4e plus c minus -4e minus c. Oh, you rock. There we go. So what happens here?
Are we distributing that middle?
You're distributing the middle negative term. Yes. So we've got a -4e, and we're subtracting that. So what's going to happen? Oh, the c's cancel. And that's an important thing I wanted you to see here, no pun, is that these cancel. So when you come up with the antiderivative, you don't need to actually worry about that constant of integration. So you can just ignore it. So what are we left with? We're left with, yeah, basically 8e. You've got 4e plus 4e, which is 8e. And if you're actually to look at the graph of this and try and make sense of it graphically or depict it graphically, I think this actually works out pretty nice. Let's draw this real quick. So let me draw that function. E is just going to be a constant function, so it's going to look like this. From -4 to 4, and this is a height of E, 0E. So really what you're trying to find there is the area, and it makes sense, right? This length is 8 times the height, which is E, 8 times E. That's your value. So wow. Now what's the big deal about that? You know, why is this such a wow experience? Well, we'll figure that out as we do the next one, or the next one, and the ones beyond that. It's going to become a lot more friendly to do these types of problems. But right now, what you need is you're going to need an antiderivative of this function. You don't have to include c, and then you're going to evaluate the function at those endpoints. So let's try the second example here, example B. So let's see, example B is going to be the integral from 1 to 3 of x squared plus 2x minus 4 dx. First thing I need to do is find an antiderivative for this. And let's do it term by term. So the antiderivative of x squared. Mage, got that one? What would that be? Yep. Add 1 to the exponent, divide by that same exponent. Cool. Antonio, let's keep going. Antiderivative of 2x. Yeah, x squared. Good. And John, how about the antiderivative of a minus 4? Minus 4x. Great. We don't have to worry about the constants, so that's it. Now, let's do ourselves a little favor. Draw a little vertical line here, and I'll put a 1 and a 3. I got to evaluate this function at these endpoints and subtract them to get the difference. So let's take a look at that. All right, so let's see. We're going to plug in, first of all, a 3 here. And let me see. Maybe do it these. I'll put in 3, a 3, and a 3. And then a 1, a 1, and a 1. So let's see. 27 divided by 3 is going to be 9, plus 9 is 18, minus 12 is 6. So this first one's going to be 6, minus 1/3 plus 1 is 4/3, minus 4. Let's see, 4/3 minus 4 is going to be what, -8/3? If you're not sure on these things, then you can take out your calculator and do these things. It's not a big deal. Do 1/3 plus 1 minus 4, and you're going to get some decimal number, but then just hit the answer to fraction key and find out that, yeah, all right, so it's -8/3. So -8/3. And when we combine that with the 6, I think you're going to get 26/3. Like that. And again, if you're not really comfortable with some of these, then you can just do it on your calculator. All right, please do it on your calculator if you're not that swift with fractions. 6 minus -8/3 is going to be plus 8 divided by 3. And then again, hit the answer to fraction key. Should be good. So math, enter twice, 26/3. Wow. Wow. That's pretty cool. Now let's remind ourselves of something here. And before I ask for a reminder, before I do the reminder, Are we okay with this calculation? This is an amazing theorem. I mean, it really is. We should do a little more fanfare for this one, so let's do it. Come on. There we go. This is so cool. I mean, take a look at how much work we did in the last section to do this problem. I mean, we started out with this. We had to go through all this. I mean, wow. And we weren't even done here, right? After all that work, we still spilled over on another page. Wow, you're replacing a page and a half. Thank you. You're replacing a page and a half worth of work with, just a couple lines. In fact, just for giggles, let's go back and compare the work with, section 5.2 to the work we do now in section 5.3, because it's a lot. We've made a substantial gain here. So let's compare that. I'm going to do it right here for comparison. So this is from 5.3. Do the integral from -1 to 2 of, whoops, still on Rocky. -1 to 2 of 4x squared plus 2 dx. Start out by finding an antiderivative. Okay, let's see. Going to add 1 to the exponent and divide by that same exponent. Alex, what would that give me, please?
4x cubed over 3.
Nice. 4x cubed over 3 plus 2x. Between -1 and 2. Wow, this is feeling easier right away. Arlie's looking at me like, why didn't you tell us this in the first place? Well, you need to have the association between area and these integrals. Let's plug in the 2 minus what happens when we plug in the -1. So I'll plug in the 2 here and the -1 here. So let's just take a look what we get term by term. This is going to be 32 over 3 plus 4 minus -4/3 minus 2. And again, I'm not giving you extra points for straining your brain and doing this stuff by hand. Let's just do it all out on our calculators. We'll do, let's clear this up. 32 divided by 3 plus 4 minus parentheses -4 divided by 3 minus 2 close parentheses. Bam, 18. Whew. Wow, take a look at that. That's a quantum leap easier than what we just did. Yes?
Is this only for linear, function?
No, this is true for anything. Anything we can find the antiderivative of. Yes, sir?
So, isn't this just dealing with definite integrals? What's the difference?
Well, this is a definite integral. I mean, the difference is that you don't have to do it this way anymore. I mean, take a look at the way we did it in section 5.2. Yeah, well, the fundamental theorem of calculus gives us a way to calculate our definite integrals. Yes. Yeah, it's a much more efficient way, provided we can get a antiderivative. Now, the one downside is that not every function is going to have an antiderivative, so that's where you run into problems. You have to do other things. So an example of something without an antiderivative would be like e to the -x squared, and that becomes a problem. We can't find an antiderivative for that thing, so then you have to struggle a little bit. But for right now, it's going to work great. Let's keep going. Let's see. So let's slide on down to example C. Oops. So this one's going to get a little messier, won't lie. So we've got the integral from 0 to 4 of 4/5. I sigh because I'm seeing a t here. I don't like the t's. They look too much like pluses. 4/5 t cubed minus 3/4 t squared plus 2/5 t, and that's all dt. Let me put a little parenthesis around this. When they get a little messier like this, my advice would be to not try and do everything at once. Try and find the antiderivative like a little piece at a time. So let's do it this way. Let's see. I'm not going to worry about the 4/5 just yet. 4/5. Let's just focus on the antiderivative of t cubed. What's the antiderivative of t cubed going to be? T to the 4th over 4 minus 3/4. And again, the antiderivative of t squared is going to be t cubed over 3 plus 2t t squared over 2. Let's close that off. One of the more common mistakes I see people doing is that they forget that you've already taken the antiderivative and they'll put another integral symbol here. But really you should put a nice straight line between 0 and 4. Now if it helps you, maybe you want to do some simplification here before we start plugging in things. So let's do that. The 4's here are going to cancel. I'll end up with t to the 4th over 5 minus t cubed over 4 plus t squared over 5. And that's still between 0 and 4. So let's see, that's going to be 4 to the 4th is 256 over 5 minus 64 over 4, which does reduce to 16, and then 16 over 5. So that's evaluating it at x equals 4. What am I going to get when I evaluate it at 0? 0. Okay, so let's clean that up a little bit. It's going to be 256 divided by 5 minus, that's just going to be 16 plus 16 over 5. 38.4, hit the math key and press enter twice. 192 over 5 would be my preferred answer. If you give me 38.4, I won't complain unless I actually put instructions that say give me an improper fraction. But either of those is fine. Whew. Okay. Let's see here. Let's keep rolling. I have to pick up the pace because I know we're running closer on time. Let me give you a little bit of a hint on D here. How are you going to find the antiderivative of the square root of x?
That makes that squared.
Yeah, you're just going to write it as x to the 1/2 power dx. Now, kind of a quick little note here for us. When you're finding the antiderivative, there's no quotient rule. I can't use a quotient rule to find the antiderivative. There's no analog of the quotient rule for antiderivatives. Can't use a quotient rule. There isn't one for antiderivatives. So a lot of times what I get is people will integrate the numerator and divide it by the integral of the denominator. It just doesn't work. So there isn't one for antiderivatives. So what else can I do then? Well, good question. 1 to 4. Let me rewrite it as 6 over x to the 1/2 plus x squared over x to the 1/2. And that's all dx. Does that help me out? Well, yes and no. I guess it depends on what you do with that. We still have a quotient. You still can't find the antiderivative of a quotient, but I can rewrite this a little bit more. How would I rewrite that? All right, 6x to the negative 1/2 plus x to what power? 3/2. Okay, now I finally got something that I can find the antiderivative of, and it's this term here. But you had to whip it into shape first. All right, so as far as finding the antiderivative here, again, maybe slow things down a little bit for yourself. So let's see, let's go up here. And that's going to be 6 times x to what power? Positive 1/2 divided by 1/2. Plus x to 5/2. 1/2, or it's going to be 3/2 plus 1 is going to be 5/2. So I'll put a 5/2 here and a 5/2 here. And finally, that's going to be between limits of 1 and 4. Now, before I try and enter this in my calculator, let's do this. When you divide by a fraction, that's the same as doing what? Multiply by the reciprocal. So multiply by 2 is going to be 12x to the 1/2. Multiply by the reciprocal here, I get 2/5 x to the 5/2 between 1 and 4. By the way, if I was looking at that and getting kind of nervous, like, yeah, I'm not sure I did that right, how could I check it? Here's a good thing, problem.
Take the derivative.
Ah, well done, James. Take the derivative. 1/2 times 12 gives me 6. Subtract 1 from the exponent gives me negative 1/2. 5/2 times 2/5 gives me 1. Subtract 1 from the exponent gives me 3/2. So perfect. So you can double check yourself as you go through these things. Now here's where it gets a little bit messy. We've got to do 12 times 4 to the 1/2 plus 2/5 times 4 to the 5/2 minus 12 times 1 to the 1/2 plus 2/5 times 1 to the 5/2. Ew, that's going to get a little bit messy here. So let's put in some numbers. Let's see. So I got a 4 from here. And then, let's see, 1 and a 1. 4 to the 1/2, that's just the square root of 4, so that's going to be a 2. 12 times 2 is going to be 24, plus 2/5 times 4 to the 5/2. That's stuff that I don't expect you to do in your head. let's see, that's going to be 32 times 2 over 5. That's going to be 96 over 5 minus 12 plus 2/5. What's that all turn out to be? Let's find out. 24 plus, oops, how about a plus? 96 divided by 5 minus 12 minus 2/5, 41.8. Kata, you getting the same thing?
Yep, 24.4.
I got 24.
Oh, it's a minus 1, not minus 12. Okay, thank you. Yeah, so let's just go back. Just kind of a quick FYI. If you make a mistake and you want to correct it, you can go back a little ways. And if you hit the second key and then the delete key, you can actually insert. I want to insert a 12 there. There we go. That looking a little bit better?
Yeah.
No, still not looking good?
Should be 24.4.
24?
Or 122 over 5.
Let's see, where am I missing something?
4 times 2 plus 2/5.
Yeah, but I distributed the negative.
Minus 2/5.
I think it should be 6.
Let's see here. So it's 24 plus 4 to the 5 halves. That'd be 2 to the 5th, which is 32. Times, oh, it should be 64 over 5. There's my mistake. This should be 64 over 5. All right, there we go. 64 over 5. Let's try that now. Plus 64 divided by 5 minus 12 minus 2 divided by 5. I did it again, didn't I?
No, yeah.
Darn it. Second 2.
Plus 2/5.
I distributed the negative. So yeah. All right. Good. 24.4. I'm just going to leave it there. I'm tired of this one. 24.4. Looking good. Let's see. This next one. What you'd have to do with that one is kind of break it up into 2 pieces. So let's take kind of a look at that. And I think I've got this one available to us here so we can look at it graphically. Yes. Ooh, that was kind of cool. So you've got what's called a piecewise function for example f here. Let's throw that one up here. So it's the integral from -2 to 4 of f of x dx. And that's going to be where f of x is 2 if -2 is less than or equal to x, less than or equal to 0, and 5 minus x squared for 0 less than x less than or equal to 4. So there's our function. If you looked at it graphically, this is what your graph looks like. And you want to find the area between the function and the x-axis for the length of that interval. So you're going to break it up into 2 parts. We're going to do this part right here, which is just the function f of x equals 2, and then the other part, which is f of x equals 5 minus x squared, like that. All right, so we'll break up that inequality, or excuse me, not break up that inequality, we'll break up that interval into the integral from -2 to 0 of f of x dx plus integral from 0 to 4 of f of x dx. Now that this is just one function in this interval, I can replace that with negative 2 to 0 of 2 dx plus the integral from 0 to 4 of 5 minus x squared dx. This one is just going to have an antiderivative of 2x between negative 2 and 0. How about the antiderivative for the second integral? Rahana? What would be the antiderivative of 5 minus x squared?
5x x cubed by j.
Nice. 5x minus x cubed over 3 between 0 and 4. This one predictably is just going to give you an area. It's going to be 2 times 0 minus 2 times negative 2. Over here we're going to get 5 times 4 minus 4 cubed over 3 minus what happens at the lower limit, which is just going to be 0. So we get 4 plus 20 minus 64 over 3. And I think that's going to be 8/3. Kate has given me the thumbs up, so we'll go with that. I'll have to talk about narcissistic numbers next time. This is kind of a cool thing. But let's just do one last one here. The integral from 0 to pi over 4 of secant squared. So let's see, where do I want to fit that one in? This is example G. I suppose I can fit it in here. Example G. The problem is really stated as find the area between the curve y equals secant squared of x between 0 and pi over 4. But it amounts to this integral. The integral from 0 to pi over 4 of secant squared of x dx. Ooh, I'm hitting you with a trick problem. At least be happy that we're not doing it the way we did in section 5.2. I can't imagine doing it that way. No thanks. Yeah, Antonio's agreeing with me. He's like, yeah, we'll hard pass on that one. Swipe left. So the big thing we need here is an antiderivative. So I'm picking your brains here a little bit. What's the antiderivative of secant squared? What do you differentiate to get secant squared? Tangent. Well done. I'm impressed because it's been a while since we've seen that. Tangent between 0 and pi over 4. So tangent of pi over 4 minus tangent of 0. Tangent of 0 is just 0. Does anyone remember what the tangent of pi over 4 is? 1. So, wow.
That was easy.
Yes. Nice. All right. All set for right now. We still have to cover the fundamental theorem calculus part 1. But we'll do that on Wednesday.